Okay, so properties of water. So we did the lab activity yesterday, and we actually visually saw some of these properties that we're going to talk about. So all organisms are about 70 to 90% water. So around 70 to 90%. You might hear some different numbers. It's kind of hard to measure the water content of something. And it can fluctuate, right? So if you're really hydrated, your water content might be higher. If you're really dehydrated, it might be lower. But about 70 to 90% for organisms. And the first organisms evolved in water. So it's a really important molecule. We evolved in it. The very first things came from it. So it's very important. It's been integrated into us. So water is really, really unique, and it has some properties that make it especially important for life on Earth. So we're going to talk a bit about the chemical structure of it. Can you all read this? Is that okay? Okay, people in the back are good? Okay, so the chemical structure of water, as you guys know, it is H2O. So it has got 2 hydrogens and 1 oxygen. And they're bound together. What kind of bond would be between those molecules? Covalent or ionic? Covalent, yeah, because it's 2 nonmetals. Awesome. Okay, so covalently bonded. And in a covalent bond, atoms share electrons. So they're not transferring like in an ionic bond, they're being shared. In water, that sharing is unequal. So electron sharing is, unequal or unequal? And that creates something that we call polarity. And I'll draw that in a second so it makes more sense. So basically you've got your oxygen. Now oxygen has an atomic number of 16, is that right? Or sorry, no, 8. Atomic mass of 16, atomic number of 8. So it's got 8 protons in the middle of it. When it is a neutral atom, it's got 8 electrons around it. Hydrogen, I should draw these smaller actually. Hydrogen, this is kind of the form that it takes. It's got an atomic number of 1. So that means it's got 1 proton in it. So I'm just putting P equals 1 in here and P equals 8 in the oxygen for the number of protons that it has. So what happens is when they share electrons, those electrons are going to gravitate way more towards this oxygen because it just has such a strong positive charge on it. So it's got 8 protons as opposed to 1. So those electrons are just going more towards the oxygen. Does that make the oxygen more negative or more positive? Negative, yeah. So if you've got more electrons, you're going to have more of a negative charge. So there's a little negative symbol there. And then the hydrogens are going to have a slight positive charge. So the actual molecule itself has got polarity, or it's polar. So it's got, slight positive charge on the hydrogen, slight negative charge on the oxygens. Okay. Can I erase that? Okay, so now because it's got that polarity, because it's a polar molecule, what actually happens when you put a bunch of water molecules together is they start to form really weak but bonds actually between the water molecules, and those are called hydrogen bonds. And I'll draw that out. So hydrogen bonds form between the oxygen of one molecule and the hydrogen of another. So what that ends up looking like, and maybe I'll just draw these in different colors, is you've got your oxygen and you've got your hydrogens. And you've got your oxygen, hydrogens. Let's draw a few of these. That was kind of like Mickey Mouse. And then what happens is you get these kind of weak, but bonds forming between the molecules. And that ends up being really important for dissolving things, and a variety of other stuff. Or I mean for surface tension. Okay. I'm just going to kind of write around this. So these bonds are weak in comparison to the actual bonds within the molecule. I'm just going to shorten hydrogen bonds to H bonds. Hydrogen bonds can form between any polar molecules. Now, a good example of this is actually DNA. So you guys remember learning about the structure of DNA and how it's this double helix shape, and then you've got those base pairs, right? Like A, G, C, and T. And we'll go over DNA later in the course as well. Okay. So the actual way that these bases are held together is through a hydrogen bond. So these bonds are important because they give water certain properties, but hydrogen bonds are also important in other aspects of our bodies as well. So yeah, this is a really good example is DNA. So DNA is held together by hydrogen bonds. All right, so water has kind of 5 main important properties that we're going to talk about as a result of this polarity and those hydrogen bonds, and it is really important to life. Okay, so the first property, we'll try to write a little smaller so I can keep this on the board for longer, is it's a universal solvent. Do you guys remember the difference between a solvent and a solute? Yeah, what's a solvent?
One of them dissolves, the other doesn't.
Yeah. Yeah, so a solvent is kind of the larger portion of a solution, and it's the thing that you dissolve a solute into. So water is a universal solvent, so it can dissolve a lot of things into it. So because of the polarity, so due to that unequal sharing of those charges, those electrons, water can dissociate ionic compounds. Large compounds and molecules that have ions in them. So put a little W for with, because I'm lazy about writing. And polar covalent substances. covalent substances, meaning other things that, like water, have an unequal sharing of electrons. Whoa. Oh, wonderful.
Thank you. So this is just added to the class right now. So she'll show up. She won't be online.
And the reason that we're saying water is a universal solvent is it can actually dissolve. It can actually dissolve more things than any other substance on the entire planet. So all right, substances, more substances. Yeah, so water can dissolve more substances than any other liquid on the planet. So that sounds like a good thing to have in your body, right? Where you want to be moving things around. Okay. I have that down twice. Okay, second thing that's really important about water is it has a very high heat capacity. Yeah.
So what determines like how like what makes sorry I'm trying to water like a universal solvent? Is it like the polarity of the breaking bonds?
Yeah, so the polarity of the water, let me kind of draw this a little bit. So we've got a hydrogen, oxygen, and two hydrogens. And then you have something that's ionically bonded together. So we've got a negative charge up here, positives down there. And then let's say you put sodium chloride in. So you've got NaCl. When you've got something that's ionically bonded, it has got, like each element has a charge on it, right? So sodium ends up with a positive charge and chlorine ends up with a negative charge. So what water will actually do, if these two are put into a beaker and mixed up together, is the oxygen molecules, because they've got a negative charge, they can actually take that sodium. And the hydrogen molecules can take the chlorine. So they actually pull ionic substances apart. So they can actually dissociate those things that are ionic. And they will also be attracting anything that's polar as well. So basically anything that has some kind of charge associated with it, when it goes into water, the molecules, we can kind of think of them as like being sticky, and they will take any polar substance or any ionic, anything with a charge and just stick to it. Does that make sense?
Yeah, so they can dissolve more substances than any other because of their unique structure.
Yeah, exactly. Yeah. There are some things that don't dissolve in water. Did you guys see one yesterday? Yeah, oil. And we'll talk about why. But basically, it's not polar. Okay, high heat capacity. So the heat capacity or the heat of vaporization, so the temperature at which water changes states is really high. So this is because it takes a lot of energy to actually break those hydrogen bonds. Or to change, I guess, is a better way to say it. Alter. They don't really break. Okay, so what is the biological significance of this? Water does things like moderate the climate. So it's hard to change the state of water. It's really hard to make it change temperatures a lot. And you guys saw this yesterday. So it's actually really great to have because it moderates our climate. So this is our biological significance. I'm not great at spelling. I'm going to be honest. I think I have this written down. Yeah, it is a C. Awesome. Okay, biological significance. So there's a few things. Moderates climate. And it helps us maintain homeostasis within our bodies. So it helps us maintain a temperature that we want to be at inside of us. So it helps maintain an internal temperature. And the other cool thing that it does is it helps us cool off with sweat. Keep on almost tripping on this chair. All right. Yeah, so those hydrogen bonds that are occurring between the actual water molecules, it just takes a lot of energy to shift those or to break them, to turn them from a solid to a liquid to a vapor. So if you think about sweating, if you've got water on the surface of your skin and it needs to go from a liquid to a gas, you are going to have to put a lot of heat into it, a lot of energy into it for it to change state. So it takes a lot of the heat of your body away with it when it changes states. So it really helps cool us down. And then it's just really good at taking a lot of heat on before changing states and before changing temperatures. So it's just great at moderating temperatures in general. Okay. I'm going to erase the first side here. This is kind of the third property. It's adhesive and cohesive. So adhesion, water is attracted to itself. It's a very narcissistic molecule, and that's because of its polarity. Oh, sorry, my bad. This is COVID.
It's early.
Okay. So adhesion is actually that it likes to stick to other surfaces. Specifically polar surfaces. And that's a result of its polarity. So anything else that has a covalent bond and doesn't share electrons equally. Okay, so why is this important? So this is actually really important in your circulatory system. We want something that is going to stick to other things and to itself as it flows through your body. So how do I work this? Excellent transport system. And we see it transporting, so we see water being transported around our body and transporting other molecules and things in your circulatory system. Does anybody know another system in your body that circulates things or moves water? Respiratory, this kind of, it brings things in for the circulatory system. It's kind of one that isn't really talked about very much, but the lymphatic system. Have you guys heard of that? No? Okay. It's pretty cool. It kind of runs parallel to your circulatory system, and basically any excess water that leaks out of your blood vessels, it's going to bring it back up to your heart. And it has a lot to do with your immune system and things as well. And it also acts as a lubricant. So it's going to stick to itself. It's going to attach to parts of your body. It's an excellent lubricant in your digestive and certain reproductive organs. And other places, but those are just two examples. Okay, fourth one is high surface tension. How many of you guys have seen a bug on water, just like running across it? Yeah. Has anybody seen those lizards that run on water? Yeah. Yeah, they're pretty cool. Those lizards that'll just like, they go really fast and they're just like, and they're running across the surface of the water. That's because of high surface tension. And high surface tension, so just the surface being kind of more supportive of things, is due to the hydrogen bonds. So the water molecules, they've all on the surface here, they've all got little hydrogen bonds in between the molecules, and they make the surface actually possible to support things on it. The significance of this, the surface of water can actually be a habitat for some organisms. This one is really cool. Water has a lower density as a solid than it does as a liquid. So do you guys remember learning in earlier grades, like you've got a solid, a liquid, and a gas, and in the solid, all the molecules are like really close together. In the liquid, they're a little more spaced apart. And then in a gas, they're just like all over the place. Yeah, and they've got more energy. They're moving around way more up here. They've got a little less energy moving around some down here. And then in a solid, they're not really moving at all. So water just likes to defy all of these things, and it actually has the atoms more spaced out in it as a solid than it does as a liquid. Or molecules, I guess I should say.
Are there other substances that also have the density as a solid?
No.
No, just
Yeah.
water?
Yeah. As far as I'm aware, I should double check that, but I'm pretty sure water is the only one. So in solid form, the hydrogen bonds create, we call it a crystalline structure. Does crystal have an H in it? No. Okay. So I'm going to get rid of this. So that's your like typical substance. And we're going to kind of look at water a little bit more. This might not be the best drawing system here, but okay, we're going to say liquid here. So in a liquid, and I'm just going to draw them as dots. You've got some energy going on in a liquid. So your molecules, your oxygen molecules are moving around. Hydrogen bonds are forming between them. So they've got hydrogen bonds going on. but they're moving around. So those hydrogen bonds are kind of like shifting and changing, going between molecules. In a solid form, they're all settling down, and those hydrogen bonds are going to be more static. So they kind of settle into this structure that the hydrogen bonds are trying to get them to settle into. But in a liquid, they're just moving around a little too much. So when it's in solid state, the hydrogen bonds are like perfectly as they want to be, and you get this kind of crystal structure. So solids, molecules are further apart. If you guys have ever frozen water and you've had like a smaller container, has it kind of like cracked it or something? Yeah, so that's why is the hydrogen bonds. Kind of wild, I think. This is also, so something that's less dense is going to float on top of something that is, more dense. So when you've got like a lake here, let's say this is a lake, and you've got some fish living in it, if you get ice forming in this, say this was your typical substance, and you had ice forming, that's a solid, and that would sink to the bottom, right? But in water, you get it freezing from the top down because that ice actually floats on the liquid water. So as the winter goes on and more freezes, this might move down, but your liquid is always going to be at the bottom, and this is actually going to insulate that water at the bottom, and things can survive the winter. So if you think about like if this were to sink and it were just to freeze like bottom up, there wouldn't be an insulating layer. Life in water wouldn't be able to survive a winter. It's pretty sweet, hey? Okay. So there's a lot of biological significance to this one. But yeah, lakes freeze from the top down. And just water bodies, I guess. Okay, lazy thing is delta T is just change in temperature. So preventing sudden changes in temperature and allowing aquatic life to survive. So now that's important for fish. In the past, we evolved from single-celled organisms in water, so it's important for our survival too. And we eat things that come from water. We're all part of the food chain, so.
So because of all of these characteristics, this is why it's really difficult to live without water?
Yeah. So really with all of these, like these kind of 5 main characteristics of water, we wouldn't be able to survive the same way that we currently are without it. So when they're looking at other planets and they're looking for water and saying like, okay, there's water on this planet, therefore there could be life. Like that's one of the main indicators that there could be life because it's just so important for every biological process, right? Yeah. It's pretty cool. Okay, so what we're going to do now is talk about how these actually like what you guys saw in your labs yesterday or in the activities that we did. And you've made observations, but we're going to add an explanation as to why those things happen and what the biological significance of them was. So for people who weren't here yesterday, we kind of had some stations set up. And we did a few things. And sorry, I don't have a handout for you all yet. I can print them later and get you some. But for now, I'll kind of write it on the board as we go as well. Okay. Was the first one the candle one, or what was station one? Candle. Awesome. Okay, so the first station was the candle. So you guys had 2 balloons. One of the balloons was filled with air. One of the balloons had a little bit of water in it. So you had like balloon number 1, balloon number 2, and then a flame underneath it from a candle. Okay, how long do you think it took for balloon number 1 to pop? Like a second, right? Like that just kind of exploded. How long did it take for balloon number 2 to pop? Yeah, and did it pop or did it like burn through? It popped. Okay, so it took like a minute for this one to pop or burn through. Yeah, which is pretty crazy. And most people just kind of held it for like 10 to 15 seconds. But thanks for testing that out for us. So what was happening in this one is the water was actually changing states into a vapor, condensing on the sides, and then coming back down. So I know that our balloons were they're opaque, right? Ideally, I guess we'd have see-through balloons and you could actually see that happening. So observations were like, I guess ideally you would be able to see that happening, but you might not have, and that's okay. Basically, it just doesn't really pop right away. What part of what we just talked about, which water property does that demonstrate? Yeah, high heat capacity. So I guess this is under our explanation and biological significance. So this is a high heat capacity. And then, yeah, what's the biological significance of having a high heat capacity? How does that impact us? Yeah, it helps us maintain an internal temperature. So if we can see that in a balloon, right, like that balloon's internal temperature is being regulated really well by the water. In the air one, it just heats up so fast and pops. As soon as you add just a little bit of water, that temperature is being maintained, and that's something that happens with us as well. Okay, the second one was water dome, right? Okay, so with the water dome, you guys had a spot plate. And you added water drops. And eventually it actually formed kind of a dome, like over top of it. So if you looked at it from the side, it actually formed a bit of a dome before it broke and just kind of went everywhere. What property of water does that demonstrate? Surface tension. Awesome. Okay, and biological significance of surface tension? Why is that helpful for life? Yeah, things can live on it. Okay, what was the third one? Sorry, I numbered these differently than I have them on here. It was the paperclip one, right?
Yeah.
Okay, so with the paperclip, ideally what happened, and I know that this didn't happen for everybody, but you had water in a petri dish and you put a paperclip in and it should have kind of floated on the surface of the water. So if you looked at it from the side, you had like water, and then as you lowered the paperclip onto it, it actually kind of forms like a little thing underneath it, like a little dip under it. But it ideally supported it on the surface. I know some of the paper clips were wet and they just sank. I didn't think about that when I put those out. But that should have happened ideally. Oh, whoops. What does that demonstrate? Yeah, same. And same biological significance. Okay, the tap water one. Trapeze tap water. So for that one, we've got a stream of water, and you're creating a static charge on a rod by rubbing it. So then this is going to have a charge on it, and as you bring it closer, does the water bend away from it or towards it? Away? Should bend towards it, ideally. I don't know, sometimes science gets weird. So the water would have actually bent towards it as you brought this charge thing in. So this has got a whole bunch of extra electrons on it. You've got a polar molecule flowing. This is going to actually, bend towards that. And again, you guys should totally watch that show on Netflix, Away, because they do this to like save the whole. I mean, it's a drama, but they do this to like save the whole spaceship with ice. Okay, so what's the property of water that we're seeing there? Pardon? Oh, adhesion? Yeah. But mostly that it's a polar substance. I guess we're kind of seeing adhesion. Well, no. Sorry, I kind of tricked you there a little bit. It's not one of like the 5 properties we went over, but just that it's a polar substance is what we're seeing. My bad, I worded that weirdly. So this is just demonstrating that water is polar. If you put a charged object near it, that does have an effect on it. And then biological significance of being a polar substance, there's a ton, right? So all of those different properties that we went over, pretty much all of them have to do with being a polar substance. So you guys could write a lot of different things for that. Okay, and the 5th station was the liquid layers. Okay, so you had a cup, you put some water and some salt in it. What happened? The salt dissolved. Awesome. Okay, and that is because water is awesome. Okay, then you had a cup of water. And you put some oil in. What happened? Where did the oil go? Yeah. So the oil actually floated. It didn't dissolve. So, oil is not a polar substance. Water doesn't dissolve everything. It dissolves more things than anything else on Earth, but not everything. And then you guys added a few drops of soap. How much soap did it take? Did anybody do like one drop at a time? No? Okay. It shouldn't take a huge amount. But basically what the soap is actually doing is creating, turning the oil into a polar molecule. So it's coating the actual oil, the lipid molecules within the oil, and turning them into something that's polar. And then, as we know, polar substances can dissolve in water. So then once the soap was added, this all dissolved. And that's why you do your greasy dishes with dish soap. And if you have an oil stain on a shirt, you can put some soap on it and like takes it out. So yeah, soap just kind of changes the actual polarity of the oil and allows it to do that. So liquid layers was just to demonstrate the universal solvent. Properties. And yeah, lots of biological significance to that one.
So when you get hydrophobic,
Yeah. So water, so oil is hydrophobic. So lipids, which we'll learn about as different biological molecules, are hydrophobic. And that's actually really important sometimes. Like in the cell membrane, what makes it up is lipids, and they're hydrophobic. So they actually maintain this like nice layer around the cell and keep things in and out of it because they're afraid of the water. Do you all remember the difference between hydrophobic and hydrophilic? Okay, maybe we should just write that down, like add this to your notes somewhere. Yeah, it's important. Thanks for bringing that up. So hydrophobic. I actually thought I had this written down in here. Yeah. So hydrophobic does not attract water. Sometimes we say afraid of water because like phobic is like a phobia. And then the opposite of hydrophobic is hydrophilic. And hydrophilic molecules can attract water. And these two terms will come up a fair amount in cell biology and the rest of the biochemistry unit as well. They're pretty important. So different molecules are going to be either hydrophobic or hydrophilic, and they'll act differently in your body as a result of that. Yeah.
so helps to make up the
Salt?
the soap helps make up the hydrophilic.
Yeah. Yes. Yeah. So the soap.
If you look at it in a microscope scale, you can still see the whole molecules there.
Yes.
Like with a soap coat.
Yeah, totally. So if we kind of like zoomed in using some like super electron microscope or something, we might see like a lipid. It's still intact, but now it's got a soap coating, and that's going to create polarity and allow it to dissolve, making it hydrophilic. Okay. Oh, and then actually, you know what? I missed a slide here while I was writing this stuff down. I missed the biological significance of universal solvents. Yep. Yeah, for sure. Just make sure you sign up here. So the biological significance of this universal solvent is it actually facilitates chemical reactions in your body via dissolved substances. And So if you think about how I drew like the sodium and the chlorine being pulled apart and dissociating in the water, those two things are then going to be way better at reacting with other substances because they've been dissociated in the water. So this is a biological significance of the universal solvent. Yeah, sorry guys, I totally missed that. Okay. Any questions around that? Can you just wait until he comes back? Pardon? Oh, it's great. Yeah, we're supposed to do one at a time. Thanks. Does anybody have any questions around those properties or like around how they apply to the things that you all saw yesterday? Yeah. Oh, sorry, our reactions. Yeah, so all about the short form. Yeah, it's useful to get used to like writing things with little abbreviations and stuff. For if you guys get into universities, sometimes they're like just talking and you're just writing and there's like nothing going on. You're just like trying to write down all the words that they say. So it's helpful to get into the habit of doing like short form that you can understand. Sweet. Okay. So